Hello and welcome back to our machine design series. Today we are diving into the world of brittle materials where failure doesn't creep in slowly but might strike suddenly and without warning. So before we jump into the theory, let me show you exactly what I mean. So I have this paper clip, and this paper clip is made from a ductile material, maybe something like a mild steel. Now watch what happens when I bend it. Okay, so see that? It stretches, it gives. You can feel that there's some warning before eventually it might break. See if I can get it to actually break. Actually, I can bend it all the way over and it still doesn't break. If I bent it back and forth a few times, it would. But that's a hallmark of ductile failure. Okay, we get permanent deformation before fracture. Now, here is a brittle material, which is a piece of dry spaghetti. And let's apply the same idea. So let me bend this until we get some failure. So you can see that I can get it to bend. If I let go, it's going to return exactly back to its original state, right? So we're not getting permanent deformation. We're getting deformation, but it's all elastic. And so if I keep going, it broke into a few pieces, just sudden fracture, right? That is brittle failure. And if you're designing with materials like glass, ceramics, or cast iron, that is the type of failure that you are going to need to predict and prevent. So that's where brittle failure theories come in. In this video, we're going to walk through three key ones. They are the maximum normal stress theory, the modified Mohr theory, and the Brittle Coulomb-Mohr theory. We'll compare how each theory handles different stress states, what assumptions they make, and how they stack up in terms of safety and conservatism. You'll also learn why brittle materials often have different tensile and compressive strengths, which theory is going to give you the most conservative design, and how to pick the right model for your next analysis or project. So, whether you're prepping for a machine design exam or designing a component that you can't afford to have fail suddenly, you're in the right place. So, let's crack on with it. Alright, so to start us off today, let's revisit our flow chart from the Introduction to Failure Prevention video. And in our last video, we talked about the failure theories on this ductile side of the flow chart. And now today we're going to talk about theories on the brittle side of the flow chart. So remember that we're defining a brittle material as one that has a strain to failure of less than 5%. And we have two options here. We can either use modified Mohr if we don't want to be more conservative, or we can use the Brittle Coulomb-Mohr if we do want to be more conservative. There's a third option, and that is the maximum normal stress theory, which is where we're going to start off today because it is the most simple, straightforward of the three brittle failure theories. So let me come down here and write this one out. Okay, so the maximum normal stress theory states that failure occurs whenever one of the three principal stresses equals or exceeds the strength. So this is going to be really the most straightforward failure criteria mathematically of any of the failure criteria that we are going to cover. All we need to know to find our safety factor is the ultimate tensile strength of the material and the maximum principal stress. And that maximum principal stress could be either the largest positive stress, biggest positive stress, or the largest magnitude negative stress. And if it is the negative stress, then we need to compare it to the ultimate compressive strength rather than the ultimate tensile strength, because we have a maximum principal stress in compression rather than tension. And remember that we are going to always order our principal stresses in order from greatest positive stress to greatest negative stress. So our failure criterion again is going to be either the ultimate tensile strength divided by sigma 1 for our safety factor, or the negative of the ultimate compressive strength divided by sigma 3. And whichever one gives you the lower safety factor, of course, is going to be your overall safety factor for your design. So, for a plane stress state, which again means that one of our three principal stresses is 0. So for a plane stress state, the principal stresses, there are just two possibilities. One is that the magnitude of sigma A is greater than the magnitude of sigma B, in which case that means that sigma 1 is greater than sigma 2 is greater than 0, or sigma 1 is greater than 0 is greater than sigma 3. In other words, sigma 1 is sigma A and sigma B is either sigma 2 or sigma 3. Then we know that our maximum normal stress failure criterion reduces to just the first equation that we've got there. So since sigma 1 is sigma A and it's greater than sigma B, we know we need to use the ultimate tensile strength to find our factor of safety. And that means that if sigma A exceeds our ultimate tensile strength, then we predict failure. Alright, and the other possibility, the only other thing that we could have, is that sigma B is greater than sigma A, which means that either sigma 1 or sigma 2 is 0, and sigma 3 is sigma B, and that is our greatest magnitude principal stress. And then we know that we need to use the second form of the failure criterion. We need to use the ultimate compressive strength. And that means that if our sigma B is ever less than the negative of our ultimate compressive strength, that negative is just there to take care of the sign because B is a compressive stress, so it's going to be negative. But if the magnitude of sigma B is ever bigger than the magnitude of our compressive strength, then we predict failure. Okay, so let's draw our failure envelope on a sigma A, sigma B plot, which is how we drew our failure envelopes in our previous video for ductile materials also. So we're going to put sigma A on the x-axis and sigma B on the y-axis. Now, for form 1 of this equation, we know that if sigma A ever exceeds our ultimate tensile strength, we predict failure. So let's look on the sigma A line and let's plot our ultimate tensile strength here. Okay, so this first form of the failure criterion tells us that if sigma A is less than, so if we are somewhere on the left side of this line, we do not predict failure, and if we're on the other side of this line, then we do predict failure. Alright, now let's look at the second one, which tells us that if sigma b is less than the negative of our ultimate compressive strength, so let's say our ultimate compressive strength is down here, plot it. Okay, there's negative SUC. So again, if we are above this line, we predict that we're safe. If we're below this line, we predict that we might have failure. And as we did in our ductile failure video, we're going to flip this over the line that is y equal to x. In other words, we're going to flip what we've done over a symmetry line where sigma A is equal to sigma B. So all we're doing here basically is we're saying that in our nomenclature, we're assuming that sigma A will always be sigma 1 and sigma B will always be sigma 3, but of course that's just nomenclature. We could flip those, and if we did, then we would essentially just flip this failure envelope over the y equals x line, or the sigma A equals sigma B line. And all that's going to amount to for this failure envelope is that we're going to have a line up here for SUT, so that if sigma B ever exceeds SUT, we also predict failure. And if sigma A is ever less than negative SUC, we also predict failure. And that's our failure envelope. Okay, so if our design, our stresses are anywhere inside of this shaded region, then we do not predict failure. It's our non-failure region. Okay, so this is the most straightforward failure envelope we're going to see. It's just a box, right? Just a rectangle. Now, for our next failure theory, we are going to have a slightly more complicated shape. So now let's move on to another failure theory. This one is the most conservative brittle failure theory that we'll look at, and that is the Brittle Coulomb-Mohr theory. Very similar to the ductile Coulomb-Mohr theory, which we covered when we were looking at ductile materials, but this one is adapted for brittle materials. So for the Brittle Coulomb-Mohr theory, we have, again, 3 scenarios. I say again, as we did for the ductile Coulomb-Mohr theory in a previous video. We have 3 scenarios. So scenario 1 is we predict failure when sigma A is greater than SUT. And we use that when sigma A is greater than sigma B is greater than 0. This, in other words, is when sigma 1 is greater than sigma 2 and sigma 3 is 0. We will use the full, longer form of the Coulomb-Mohr theory for this next scenario, which says that sigma A over SUT minus sigma B over SUC is greater than or equal to 1. If that criterion is achieved, then we predict failure. And we will use this when sigma A is greater than 0 and sigma B is less than 0. So in other words, this is when sigma 1 is positive and sigma 3 is negative, sigma 2 is 0. And finally, we will use this last form of the Coulomb-Mohr theory. We predict failure when sigma B is less than negative SUC, when sigma 1, or sigma 1 is 0, and then sigma A and sigma B are both negative. And then I'll write the factors of safety over here just so that you have them. So for the first form of the equation, our safety factor is SUT over sigma A. For the second form of the equation, 1 over our safety factor is equal to sigma A over SUT minus sigma B over SUC. And for the last line, our safety factor is equal to negative SUC over sigma B. Okay, so that is our Brittle Coulomb-Mohr theory. I'm going to go ahead and write out the failure criterion for the modified Mohr theory, which is just another modification of the Mohr theory for brittle materials. And then after I write this out, we'll plot all 3 of the failure theories on one sigma A, sigma B plot to compare the failure envelopes. Okay, so when sigma A is greater than SUT, we predict failure, as we did before. Okay, so this is the same as the Brittle Coulomb-Mohr. And then I'm going to go ahead and write the other line that is the same as Brittle Coulomb-Mohr, which is that we predict failure again when sigma B is less than negative SUC. And we'll use that again when sigma A and sigma B are both negative. Okay, and now we have something a little bit different. So for the modified Mohr theory, we're also going to use sigma A greater than SUT as a failure criterion when we have sigma A greater than 0 and sigma B less than 0. So when sigma A positive and sigma B negative, and both of these criteria have to be true, and the magnitude of sigma A is greater than the magnitude of sigma B. Okay, so those are absolute value signs. So the magnitude of sigma A has to be greater than the magnitude of sigma B. And then lastly, when we have sigma A positive, sigma B negative, and the opposite, we have greater magnitude of sigma B than sigma A, we're going to use another form. So it's a bit of a longer equation. We have SUC minus SUT times sigma A divided by SUC times SUT minus sigma B over SUC if all of that is greater than or equal to 1 under the condition that sigma A is positive and sigma B is negative and sigma B is greater in magnitude than sigma A. All of that is true, then we predict failure. So, as promised, let's take a look at what all of this actually looks like in a failure envelope. Well, before I do that, let me make sure I write out for you the factors of safety for each of these lines. Okay, now let me copy and paste what we had up here. Let's start a new page. Alright, so this was our maximum normal stress theory right here. There's maximum normal stress. Move that over actually. It'll be less confusing if it's over here. Alright, now let's take a look at some of these other theories. So we'll start out with the Brittle Coulomb-Mohr theory. We have less to deal with there. So for the Brittle Coulomb-Mohr theory, and let's color code this one green maybe, we have sigma A greater than or equal to SUT when sigma A and sigma B are positive. So when sigma A and sigma B are positive, we're in this quadrant. And for Brittle Coulomb-Mohr, we know that we predict failure only if sigma A is greater than SUT. So if we're on the other side of that green line, we predict failure. So same as the maximum normal stress theory so far. Now let's look at our bottom line actually. Let's just skip down to the bottom because it's easier. So when sigma B is less than negative SUC, we also are going to predict failure. So that's this line over here. If we're below that green line, then we predict failure. If we're above it, we predict that we're safe. And now let's look at the line in between. We have this equation, and this equation is just a straight line. It's a linear equation in terms of sigma A and sigma B. And once again, you can prove this to yourself later, but I'm going to promise you that it is a straight line that connects the endpoints of these other two flat lines we've already drawn. So that is one side of our failure envelope, and again we can flip that over the y equals x line or the sigma A equals sigma B line to complete the full picture. And so doesn't that look a lot like the Tresca criteria? It's similar, right? Except that now we have different values for SUT and SUC. So we could have a more elongated look, or a larger, you likely would have a larger SUC side than what I've drawn here. Usually compressive strengths are greater than the tensile strengths. And maybe I'll draw one more form of this before we wrap up the video. But before I do that, let's draw the modified Mohr theory in here. So let's color code this one, make it blue. Alright, here's our modified Mohr theory. So again, the top two lines are going to be the same as Brittle Coulomb-Mohr, and those top two lines are this line and this line. So once again, those are the same for all three theories, those two lines. And we could even go ahead and flip it over the y equals x line and say that we know we're going to have this right angle in the first and in the third quadrants. Alright, now, but what happens with our other lines here? So for this third line, we're going to continue the straight line from this top one up until the point where sigma A and sigma B are equal to one another, which, in other words, it's going to continue until we cross over the line of SUT. And for that reason, it probably would make more sense to draw this in an elongated way, because this is going to look kind of funny otherwise. So let me fix this really quick. Alright, there we go, that's better. Sorry about that, but I think that this is going to help everything make a little bit more sense. So, as I was saying, we need to find where SUT is on our y-axis, on our negative y-axis. So let's draw a line about here, and this is at negative SUT. Okay, so at this point, our modified Mohr theory is still the same as the maximum normal stress theory. Okay, we're just going to continue that straight line down. I mean, if we take a look again at this failure criterion, it says that sigma A is greater than SUT is our failure criterion, so that's that same vertical line. In that quadrant where sigma A is positive and sigma B is negative, as long as the magnitude of sigma A is greater than the magnitude of sigma B. Okay, and the magnitude of sigma A is going to be greater than the magnitude of sigma B up until this point. And at this point now, sigma B is going to be greater than sigma A. And when we reach that transition point, we now are going to use this line here. And so now this line is again going to be a straight line in terms of sigma A and sigma B. And I'm just going to go ahead and tell you, and you can prove it to yourself later, that this line connects the end of this line to the end of this line. All right, and again, we can flip that over the y equals x line. All right, and there are our 3 failure envelopes. So the largest one, the maximum normal stress theory, it covers this full rectangle. All right, and then we have the modified Mohr theory, which is the next failure envelope in. So the size of the failure envelope essentially tells you the level of conservatism also. So the maximum normal stress theory is going to be the least conservative of our 3 failure theories because it is the largest failure envelope, right? So if I had a point, for example, a stress state that was down here, then with the maximum normal stress theory, I would predict that I was safe. Whereas with modified Mohr or with Brittle Coulomb-Mohr, both, I would predict failure. Okay, and then Brittle Coulomb-Mohr here is our green line. And that failure envelope is, again, smaller than the other 2. And so that one is going to be our most conservative failure theory. Okay, so it goes Brittle Coulomb-Mohr, most conservative, then modified Mohr, then maximum normal stress is our least conservative. This is important because maximum normal stress is a commonly used failure criterion as just a first check, and that's okay, right? Especially if you're in this first quadrant or this third quadrant, you're going to have the same answer as you would using either of the other 2 theories. But if you're in this second or fourth quadrant and you're using maximum normal stress theory, there's a chance that you are being not conservative enough in your estimate. As far as accuracy goes, the modified Mohr theory is probably the more accurate theory for most materials. And then Brittle Coulomb-Mohr is useful in that it is just more conservative. So if you want to build more conservatism into your estimate, then using the Brittle Coulomb-Mohr theory is a good way to do that. Also, it's easier to use than the modified Mohr theory. You have less conditions that you need to deal with. And then, of course, maximum normal stress theory is useful in that it's so easy in its application. All right. So that's going to wrap it up for this video. I hope that this was helpful in understanding brittle failure materials or brittle failure mechanics and the different failure criteria that you could use for these brittle materials. And in the next one, we'll start doing a little bit of fracture mechanics. So in my course, I just do a small introduction to fracture mechanics. We're not going to dive super deep into it. There's a lot that you could do with fracture mechanics, but we won't do too much. We'll just get a quick introduction, and then we'll start talking about fatigue, which is always an interesting topic. So I hope you're looking forward to that. Thank you for watching, and hope to see you in the next one.